This video brought to you by Angry Lego Samurai. I think that's a woman, actually. Not that it matters. Okay, so what we're doing in 7.3 is we're going to prove trig identities. So I think one of the important things is to make sure we understand what does it mean to be an identity. So an identity here, or really mathematics in general, is something that's all true, that's always true for all values of x, or all values within the domain. For example, sine of x equal to 1/2 is not an identity because it's only true for specific values of x. Those values happen to be the inverse sine of 1/2, or if you recall from a unit circle, let's see, where is sine equal to 1/2? It feels like right here, which would be pi sixth. So x would be pi 6, or over here on this side, 5 pi 6. And then, of course, any 2 pi thing, 2 pi units from that point. So this is not an identity because it's only true for a few values of x within the domain of sine. On the other hand, if I give you sine squared x plus cosine squared x equals 1, this is true for any value of x within the domain of sine and cosine. So this is an identity that is always true. It's true for any x value. All right, so what do we mean when we say something's proven in everyday language? Well, it tends to be, let's say, a collection of facts, and we can't, at this day and age, a lot of us want to argue about what are facts, but a collection of facts that are stitched together to create an argument. In that nature, and so the overwhelming preponderance of facts proves that something may or may not be true. In mathematics, we use, say, definitions and previously proved theorems and axioms and what are the other things? All these other different kinds of things that all are put together. They're building blocks to prove new things. So we're going to use this, probably can't pronounce this right, approach when we prove identities. So all identities are equations. We'll manipulate one side of the equation until it becomes the other side of the equation. That is typically the best strategy. You don't want to be manipulating both sides of the equation because you might be going in opposite directions. So here's some tips. You can read through those. We could start listing as many as we know. If you look at your reference sheet at the back of your course pack, or at the front, I believe, I think it's yellow, you're going to see a ton of identities listed there. So here's our first one. We want to prove that secant x minus sine x times tangent x is equal to cosine x for all values of x within the domains of those functions. So I think one of the suggestions on the other side is to start with the most complicated side and try to turn it into the least complicated side. So let's do that. I'm going to take secant, sine, and tangent, this left side, and I'm going to rewrite everything in terms of sines and cosines. I know that secant is 1 over cosine x. And then that sine x, because tangent is a fraction, I'm going to write it as over 1. And this will be times sine x over cosine x. That's our identity for tangent. And then this is going to equal cosine x. Now, I'm not going to write this again until the end because it just gets redundant, because I'm going to do all the work over here. So if you look at this, we'll multiply this fraction together. I'll have 1 over cosine x minus sine squared x over cosine x. Okay, so I'm then going to subtract these fractions using our work with fractions. So this just becomes 1 minus sine squared x because those denominators are the same for cosine x. And then you may recall, I believe it was back in 7.2 or 7.3, we noted that cosine squared x is equal to 1 minus sine squared x. That's just taking that Pythagorean identity and solving it. Now, we can take identities that have already been proven and move things to the left and right of the equation because we know it's true. We can't do that here. For instance, I can't subtract secant x from both sides of the equation because we're trying to prove that this is true. Okay, so that means I can just take this sine squared, 1 minus sine squared x. It is exactly cosine squared x. Excuse me. And, oh, we're there, right? Because cosine squared divided by cosine is just cosine x. And so, hey, isn't that exciting? We've proved our first trig identity. This is why I became a math major, these exact things. All right, let's do one more, and then we'll take a push-up break. So this is kind of a tricky one of deciding which side is more complicated than the other, I suppose. I'm going to go ahead and mess with this one. And I'm going to use the same strategy I did above. We're going to rewrite tangent and cotangent in terms of sines and cosines. One of the things that can be frustrating for students with these types of problems is that there's not one set way to solve these identities. So really, what you want to do is just kind of play with them and see if you get anywhere. Start rewriting them in terms of different identities that you know, and see if it gets you anywhere. Okay, so for this one, since I've solved this multiple times, I kind of know this one strategy. What I'm going to do is go ahead and add the fractions in the numerator and the fractions in the denominator. So what I need is a common denominator, so I'm going to have to multiply this by cosine y over cosine y. Then I get a common denominator. I need to do the same thing here, sine y over sine y. Note that we're just kind of treating these as two separate things here. So I'm going to skip a step here. Because we're ending up with the same denominator, this fraction becomes cosine plus sine all over cosine. That's our numerator. So cosine, oh man, I keep messing it up. Cosine y plus sine y all over cosine. Note the denominator becomes sine plus cosine all over sine. Of course, that the order that we're adding those things doesn't actually matter, but anywho. All right. Again, this is supposedly all equal to secant over cosecant. Now, you know how to divide fractions from your work with algebra. You multiply by the reciprocal of the thing you're dividing by. So this becomes, leave that numerator as it is, cosine y plus sine y all over cosine y. And it's now going to become times sine y all over sine y plus cosine y. Now check this out. This numerator, cosine plus sine, is the exact same factor as this denominator, sine plus cosine. You may not believe me because they're in a different order, but remember 3 plus 4 is the same thing as 4 plus 3. So these are exactly the same thing. We divide them away, they equal 1, and then we end up with sine y over cosine y. Well, that's not this, right? So now let's either rewrite these as what they are, or I think actually what's going to be better is to now mess with this. So what we can note is that secant is 1 over cosine y, and cosecant is 1 over sine y. And now we do the same thing we did here. We flip and multiply. So this becomes 1 over cosine y times sine y over 1. What? There it is, right? Multiply across, and this becomes sine y over cosine y. I apologize, this got a little messy in terms of the layout. But we have just proved that 1 plus tangent divided by 1 plus cotangent equals secant over cosecant.